Hi students, today we're going to study about alternating current. In the chapter electric current, we had studied about DC current. Remember, the kind of current which just keeps on flowing regularly when a constant voltage source is connected to a circuit? In alternating current, the current is initially slow, like this. Then it speeds up, and then it speeds up further. Then it becomes slow again, and then it becomes slow yet again. So what is this alternating current? It's a type of variable current, but what is the exact formula for alternating current? We'll study about all that in this chapter related to alternating current. We'll also study that in case of direct current, or the current that we studied up till now, the current was constant like this with respect to time. Alternating current is something like this. It varies sinusoidally with time. Alternating current. Let's unravel all its mysteries today. Here we go. First of all, of course, we'll come to the basic question. What is alternating current in the first place? Current flowing through an element changing its direction periodically is called alternating current. Understood? So as you can see, the current flowing through this red wire is firstly increasing in speed, then it keeps on increasing in speed, then it decreases, and then it further decreases. The point here is that the intensity of the current keeps on changing with time, and the change is periodic. So what that means is, say every 2 minutes or every 10 minutes or every n seconds, the current undergoes the exact same change, in its direction and magnitude. So for example, this graph depicts an alternating current. As you can see, in this graph, the equation of the current or voltage variation with respect to time is either I0 sin omega t or V0 sin omega t, isn't it? As you can see, the current or the voltage here are varying sinusoidally with time, isn't it? So such a current is called alternating current. Now why is a varying alternating current used? Like, why are we not happy with the current that we studied about in earlier chapters, the direct current? Alternating current is used because it's practically very feasible to transport alternating current from the place where it is produced to our homes, and alternating current is much safer to finally bring to our homes from the generation station. Understood? You see, in the case of alternating current, the transmission of alternating current through the wires is high voltage transmission, but when we bring that current to our own house, we can actually step down the transmission voltage to around 230 volts, and we can provide safe current in our houses and light up bulbs and tube lights. There's a special device called transformer which actually reduces the high voltage of alternating current that's transmitted in wires to 230 volts for use in our homes. The problem with direct current is that there is no such special device which reduces the high voltage used in transmission to low voltage. So that means that if we use direct current, say from huge battery sources, and transported them to our houses, then we would have to actually light our bulbs and our tube lights at very high voltages, like voltages of 10,000 volts or say 5,000 volts. Now such high voltage is very dangerous. Such voltage would even ionize so many things near the wires. So that is the reason we use AC current, because it's easier to convert high voltage AC to low voltage AC for easier use in our houses. Understood? So that was the brief explanation of why alternating current is generally used in our house. Now we come to something very interesting. Okay, we've heard that alternating current is current which varies with time periodically. The current increases, the current decreases, the current increases and decreases again. However, how is alternating current produced? You see, in the case of direct current, some chemical reactions take place in a battery. Because of these chemical reactions, electrons flow from one part of the battery to another part of the battery. In case of alternating current, however, how do you produce a current which varies sinusoidally, or say, as a cosine function with respect to time? How do you regulate that? Alternating current is generally produced by this method I'm going to tell you about. You see, if you take two magnets as shown. The green bodies shown in this figure are magnets. In that case, a magnetic field will act from, one body towards another body. Now, if you rotate a coil in between these two magnets and in the magnetic field, then when you look from the top, this is the view that you will get, isn't it? This coil actually extends inside your screen. Understood? For example, this is how the magnets are actually placed. Something like this. And the coil is actually rotating like this. This is how the coil is. And it's rotating like this. And we are showing you the top view here. This is the top view. If you look at this whole setup from the top, that's the view you see here. Understood? So when a coil rotates like this as shown, in that case, when it makes an angle theta with the vertical, then the net magnetic flux, passing through the coil is Bs cos theta, isn't it? Now, if this coil actually rotates with an angular velocity omega, in that case, the angle theta that it covers in time t will be omega t, and therefore the net flux passing through this coil at any time t will be Bs cos omega t, isn't it? That's because the angle between B and S, the angle between the magnetic field and the area vector of the coil, is omega t or theta, isn't it? Now, if the flux is phi equal to Bs cos omega t through the coil, then clearly at times we use the complex number system to actually depict, impedance values better. For example, we assume that the x-axis is the real axis and the y-axis is the imaginary axis. In that case, whenever we're drawing phasors, we're drawing them either along the real axis or along the imaginary axis, isn't it? So R, the resistance, is along the real axis. XL and XC are along the imaginary axis. Similarly, the current initially is along the real axis. So we can just write Z, the impedance, as R plus omega L minus 1 upon omega C, J, isn't it? So the real part of Z is R, and the complex part of Z is omega L minus 1 upon omega C, or XL minus XC. So that is how we can represent the impedance in the form of complex numbers. Now this is just a depiction, and you don't need to worry about how exactly you can represent the impedance in the form of complex numbers. You see, this just simplifies the calculations when you have to add two impedances, subtract two impedances, or even depict the reactance because of inductors and capacitors and the resistance reactance. Okay, so it's quite easy to depict it this way, rather than always saying that the magnitude is square root of r square plus xl minus xc whole square and tan phi is this expression. Instead of saying all that, you can depict the impedance like this. Let's now finally solve an IIT JEE 2003 problem. You see, we have to get a hang of what's happening. This IIT problem will really clarify what's happening. When an AC source of EMF E equal to E0 sin 100t is connected across a circuit, the phase difference between the EMF E and the current I in the circuit is observed to be pi by 4 ahead. If the circuit consists only of possibly RC, RL or LC in series, then what is the value of R or L or C? This graph was also given in the question. The graph shown. The options given in the question were these: option A, option B, option C or option D. So what was happening in this question? What did they ask? What was the data given? Now the first thing that is mentioned in the question is that there's an LR or LC or an RC circuit. They haven't told us, they haven't said there's an LR circuit or they haven't said there's an RC circuit. It could be either of these circuits. Then they have told us that in this circuit, phase difference between the current and the voltage is pi by 4. And then they've given this graph, this blue line indicating the graph of the current with respect to time, and E indicating the variation of the voltage with respect to time.
Then they have asked us to find out the magnitude of the resistance and inductance, or the resistance and the capacitance. Understood? Depending on whether it's an RL circuit, LC circuit, or an RC circuit. Now the first thing we can make out from this graph here is that the current leads the voltage by pi by 4, isn't it? That's because look at this cycle of the current, this one. Here, the current rises, then it falls down, then the current assumes a maximum negative value, the current becomes 0. So this cycle here, this same cycle, in the case of the voltage, starts late, isn't it? For the voltage, the cycle starts here, the same exact cycle. So as you can see, it starts pi by 4 late, and therefore you can say that the current leads the voltage in this case. Now if you draw the phasors for the potential difference across the resistance, the capacitance and the inductance, you will see that the current leads the net potential difference only in the case of an RC circuit, isn't it? After all, in the case of an LR circuit, the potential difference value will be somewhere here, isn't it? In this region, in the upper quadrant, and therefore the potential difference will lead the current. Only in the case of an RC circuit, the potential difference will lag the current by a certain angle. So we can therefore say that this is an RC circuit, and therefore the potential difference lags behind the current by 45 degrees, isn't it? Again, tan 45 degrees will clearly be XC by R, isn't it? Instead of representing the phasors ER, EC and I, we can replace ER phasor by R phasor and EC phasor by XC phasor. In that case, tan 45 degrees, which is EC by ER, will be XC by R. Now XC is 1 upon omega C. So 1 or tan 45 degrees becomes 1 by R omega C. Now we are already given the value of omega, isn't it? And since the value of omega is already given, we get the value of RC as 1 by 100 per second. Now the point is that we are given different values of resistance and capacitance in the question. We can actually check that for which values the value of RC comes out to be 1 by 100. Let's consider all these options and see for which option RC is 1 by 100. That option will be the correct answer. Clearly option D is wrong because it's not an RL circuit but an RC circuit. C is also wrong. Option B is also wrong because the product of R and C in this case comes out to be 10 raised to minus 3 per second. In the case of A, however, the answer comes out to be perfect. That is 1 by 100 per second, and therefore option A is the correct answer because the product of RC is 1 by 100 in this case. So as you saw, all this IIT JEE problem really involved was the concept of phasors and the fundamentals of calculating the resultant voltage. If you have different phasor vectors for different voltages across different elements in your circuit. Let's now move on and solve another IIT problem. This one was asked in 2004. In an LR series circuit, a sinusoidal voltage V equal to V0 sin omega t is applied. It is given that L equal to 35 millihenry, R equal to 11 ohms, Vrms equal to 220 volts, omega by 2 pi equal to 50 hertz, and pi equal to 22 by 7. Find the amplitude of the current in the steady state and obtain the phase difference between the current and the voltage. Also plot the variation of current for one cycle on the given graph. This question really seems bamboozling, when you look at it first. What is actually happening here? Well, there's nothing really complex. You see, you're basically given an LR circuit. There's this alternating current voltage source. There's an inductor and there's a resistance. Now in this question, all that we really need to calculate is the electric current flowing through the circuit. How do we calculate that? Well, Vrms is given, isn't it? And Irms is Vrms divided by Z. There's no doubt about it. So we have to calculate, the net impedance of this circuit. When we have done that, we can simply say that IRMS is VRMS by Z, isn't it? And similarly, we can also try to calculate the phase angle by which the voltage leads the current, by drawing phasors. So first of all, let's see what's happening by drawing a phasor diagram. As you can see, VR, the potential difference across the resistance itself, and the current are all along the x-axis initially, the phasors I mean. Similarly, the potential difference across the inductor initially leads the potential difference across the resistor by 90 degrees. So does the value of XL, the inductive reactance. And this is the value of Z, isn't it? So as you can see, impedance is somewhere between XL and R here. It's in the top quadrant and it leads the current. IRMS is VRMS by Z. Now Z is clearly square root of R square plus XL square from this diagram, isn't it? After all, the phasor vector for Z is square root of R square plus XL square, the magnitude. And VRMS is known, and R is known, and XL is known because XL is omega L and both omega and L are given in the question. Therefore, by substituting all these values, we get the net value of the root mean square current as 20 by root 2 amperes. Now this is the value of the root mean square current. What is the exact expression for the current in terms of time in the form A sin omega t plus phi? What's the exact value? So since IRMS is 20 by root 2, the maximum value of the electric current must be root 2 times the RMS current, isn't it? So you can say that I naught, the maximum value of the current, is 20 amperes. The angle phi clearly comes out to be XL divided by R, isn't it? That is obvious from the diagram. Tan phi is XL by R. Now the value of phi interests us because you see it is given that V is V naught sin omega t, isn't it? So if we know the value of phi, then we can say that I is I naught sin omega t minus phi because the current lags behind the voltage by an angle phi, isn't it? So we can clearly be able to write down the expression for electric current if we know the value of phi. From the phasor diagram, tan phi is XL by R. The value of XL is known, omega L is known, the value of R is given. So the value of tan phi comes out to be 1 or phi comes out to be 45 degrees. And therefore you can say that the net value of electric current at any instant t is I equal to 20, the maximum value of current, into sin omega t minus pi by 4, isn't it? After all, V is V naught sin omega t, and since the current lags behind the voltage by pi by 4, I is I naught sin omega t minus pi by 4. Omega is already given to be 100 pi radians, and I naught was what we just determined as the maximum value of current, equal to 20 amperes. So that's the answer to this IIT JEE problem. The problem also asked us, to depict the variation of electric current on the same graph on which the voltage variation has already been depicted, isn't it? Now the equation for the voltage is 220 root 2 sin 100 pi t, isn't it? Because omega is 100 pi and the RMS voltage is 220 volts. So the maximum voltage is 220 root 2. Now we can similarly plot, the electric current on this graph. I is 20 sin 100 pi t minus pi by 4. Again, as you can see, the cycle for the voltage starts at the origin. The same exact cycle for the current, this one starts slightly later in the case of the electric current. It starts at a phase angle later. Understood? You can even label all these points at which the electric current graph intersects the time axis, isn't it? So you can see, that the electric current is 0 at time period divided by 8, and then it increases and increases, and it again becomes 0 at 5t by 8. T here represents the time period of both the electric current and the potential difference variation. How do you calculate, that the electric current touches the time axis at t by 8, 5t by 8, 9t by 8? You see, we already know that the electric current lags behind the voltage by pi by 4. Lagging by 2 pi basically means lagging by one time period. So lagging by pi by 2 means lagging by t by 4, and lagging by pi by 4 means lagging by t by 8. Understood? Lagging by 2 pi means lagging by one time period, because the period of the voltage and the electric current, these functions, is 2 pi. Therefore lagging by pi by 4 means lagging by a time t by 8, and therefore the electric current cycle starts t by 8 later. Understood? That's how we can obtain the values of t by 8, 5t by 8 and 9t by 8 here. So that was our IIT JEE problem. Let's move on to the next concept.
There's a special phenomenon called resonance that occurs in both series and parallel AC circuits. What is this resonance phenomenon? You see, we know that the magnitude of Z is square root of R square plus XL minus XC whole square, that is omega L minus 1 upon omega C whole square. Now as we keep on varying the frequency of the voltage and electric current, the frequency of the voltage and electric current simply means the number of cycles per second, the number of times per second that the same variation keeps repeating. So as we keep on varying the value of omega, the value of Z changes, isn't it? There's no doubt about it. So if you plot a graph of Z with respect to omega, you obtain a graph like this. This is the graph of this expression above. What you can see here is that the value of Z is minimum when Z is equal to R. Interesting, isn't it? This is what happens when you sketch this graph. That's what you uncover. Now this condition when Z is minimum is actually called the condition for resonance. The resonance condition actually represents the condition where the net reactance of the system is zero, the inductive reactance as well as the capacitive reactance. So in the case of resonance, only the resistance acts in the circuit. The current is simply V by R. The inductance and the capacitance do not contribute to the impedance. Now XL equal to XC, isn't it? After all, if Z minimum is R, then omega L must be equal to 1 upon omega C. XL must be XC, and therefore you can say that in this case, since omega L is 1 by omega C, omega is 1 by root LC, and therefore condition for resonance is that the net angular frequency of the circuit should be 1 by square root of LC. I have written omega naught here because omega naught represents a very special value of the angular frequency such that Z minimum is R, isn't it? So when omega naught is 1 by root LC, the net impedance of the system is only R and resonance occurs. Now since omega is 2 pi f, you can say that the resonant frequency is 1 by 2 pi square root of LC, isn't it? So that also you must remember. The series resonance circuit is often called acceptor circuit. This is because the impedance is minimum at resonance, isn't it? So it accepts this omega naught frequency out of all the other frequencies. If the series circuit is given a choice that you can accept any frequency, say omega 1, omega 2, omega naught, omega 3, omega x. In that case, the series circuit actually accepts only one frequency, omega naught. And that is because the impedance, or in a way the resistance to the flow of current, is minimum for omega naught, isn't it? And since it accepts that one frequency at which impedance is minimum, it's called the acceptor circuit. If all this sounds very vague, don't worry. Just remember the line that I have told you just now. You don't need to go deep down into exactly why it's called an acceptor circuit. Acceptor circuits, however, are also used in radios. So in case of radio signals, you have to detect one signal and neglect all the other signals. So which signal to detect basically depends on the resonant frequency. Understood? So different stations have different resonant frequencies. So there you go. Now a special factor in a resonance circuit is the Q factor. Q factor, or in a way the quality factor, indicates the quality of the resonance. Basically, we know that VL
The potential difference across the inductor is I times XL, isn't it? The inductive reactance. Therefore, VL can also be written as V by R into XL. I have substituted I by V by R here because clearly we already know that VL minus VC is 0, isn't it? And XL minus XC is 0. And therefore, we can simply say that only the resistance is active in the circuit. So V by R is the current. So VL is V by R into XL. In the case of a resonant circuit, Q factor is defined as the ratio of the net potential difference across the inductor divided by the net potential difference applied in the circuit. Understood? So VL divided by V is called the Q factor, and of course it determines the quality of the resonance. Now VL by V is XL by R. So VL by V is the same as the inductive reactance divided by the resistance in the circuit. And this is the quality factor of the circuit. It determines also the sharpness of the resonance. If the quality factor is high, that means the resonance is very, very sharp. Now you don't need to go into the details of what exactly sharp resonance means, but basically the overall idea is that the inductive reactance divided by the resistance gives you the quality factor. And the more the inductive reactance in comparison to the resistance, the sharper the resonance. So that was about resonance and the quality factor. And after studying so much, won't we solve a problem? Of course we will. A series LCR circuit containing a resistance of 120 ohms has omega equal to 4 into 10 raised to 5 radians per second. At resonance, the voltages across the resistance and the inductance are 60 volts and 40 volts respectively. At what value of omega does the current lag behind the voltage by 45 degrees? This question definitely seems confusing. It's an LCR circuit and two different conditions are given in the question. Omega is 4 into 10 raised to 5 and a certain condition is given. Then we're asked, what the value of omega is so that the current is behind the voltage by 45 degrees. Again in this question, we are basically given an LCR circuit, something like this. Now, finally, what is it that we need to calculate? We need to calculate the value of omega such that, the voltage lags behind the current by 45 degrees. Now, we know that if the voltage lags behind the current by 45 degrees, Z, the impedance also lags behind the current by 45 degrees, isn't it? In fact, the impedance lags behind the resistance by 45 degrees, isn't it? So we can simply say, tan 45 degrees is XL minus XC divided by R. We can use some formula like that. We can draw the phasor for impedance, resistance and 45 degrees, and we can somehow use the formula tan phi is XL minus XC by R to calculate the value of omega. The problem is that in this case L and C are not given. We need to know the value of L, the inductance and the capacitance when we write the expression omega L and 1 upon omega C. So to calculate the value of L and C, the first part of the question is given. The first part of the question says, that at resonance, the frequency is 4 into 10 raised to 5 radians per second. It also says that at resonance, the potential difference across the resistor is 60 volts. The resistance is 120 ohms. The potential difference across the inductor is 40 volts. Now, we can calculate the inductance L by equating the current through the resistance and the inductance. That is because, since this is a series circuit, the current through the resistance and inductance is the same. The current through the resistance is clearly VR divided by R, isn't it? VR is 60, so 60 divided by 120. The current through the inductor is clearly VL divided by omega L, isn't it? VL is 40 volts, omega naught is 4 into 10 raised to 5 radians per second. So when we substitute these values, we get 40 by omega naught L is 60 by R. On simplifying, L comes out to be 0.2 millihenry. So there we go. We have determined the value of the inductance. The next thing we need to do is determine the value of the capacitance. But we already know that in case of resonance, omega naught is 1 by root LC. Now L is known and omega naught is known. So the value of C here comes out to be 3.125 into 10 raised to minus 8 farads. And so we have determined the value of L and C. Now it is given that the voltage leads the current by 45 degrees. Now if the voltage leads the current by 45 degrees, clearly we can say that the impedance leads the resistance by 45 degrees. And tan 45 degrees is XL minus XC divided by R. Now XL minus XC divided by R is clearly omega L minus 1 upon omega C divided by R. L is known, C is known, tan 45 degrees is known and R is known. And so the value of omega for which the voltage leads the current by 45 degrees comes out to be 8 into 10 raised to 5 radians per second. And that is our final answer. Let's now move on to the next concept. We just studied, a series resonance circuit. So we calculated the condition for resonance in a series circuit. In an AC parallel circuit, the condition for resonance is different. So you can, assume this circuit which has an inductor and a resistor in series, and it has a capacitor in parallel with the inductor and resistor. Now let's calculate the condition for resonance in a parallel resonance circuit. In a parallel circuit, current I flows from the voltage source. However, unlike in a series circuit, the same current I does not flow through the resistance, the inductance and the capacitance. As you can see, it breaks up into two parts, IL and IC, the current through the inductor and the current through the capacitor. Now, the method for calculating, the condition for resonance in a parallel circuit is to equate the net reactance of the system to 0. You see, if we can calculate the net impedance of the system and if we then equate the net reactive component of the impedance to 0, we will get the condition for resonance, because resonance is that condition when the net reactive component of the system is 0. Now clearly, if you assume that Z1 is the net impedance due to R and L and Z2 is the net impedance due to C, then Z will be Z1 Z2 divided by Z1 plus Z2. After all, both Z1 and Z2 are in parallel. Now we can use the complex number notation for representing Z here. The reason is that if we use a complex number notation, then in the final answer we can equate the imaginary part of the complex number to 0, and when we do that we'll get the condition for resonance. So it's quite easy to use the complex number notation here. So there you go. As you can see, Z1 is R plus j omega L, isn't it? And Z2 is 1 by j omega C, isn't it? And you can substitute Z1 and Z2 by these expressions. As you can see, the denominator is Z1 plus Z2. So the denominator becomes R plus j omega L plus 1 by j omega C. Understood? Now, rationalize the denominator here. What does rationalizing of the denominator mean? Rationalization of the denominator means that you simply multiply the denominator, by its complex conjugate. For example, if the denominator has a plus iota b in a complex number, you multiply the denominator by a minus iota b. In that case, the denominator becomes purely real. Now we are trying to rationalize the denominator, because if the denominator becomes purely real, in that case, it will be easier to put the net complex part of this expression to 0 in the numerator, isn't it? When we rationalize, this is what we get. As you can again clearly see, this is the real part of Z and this is the imaginary part of Z, beyond J. Now when we put the imaginary part of Z to 0, that is, when we put this part to 0, what do we get? We get this condition. And this is the condition for resonance in case of a parallel circuit. Omega naught is square root of 1 by LC minus R square by L square. Of course, you have to remember this expression as it is very, very important for competitive examinations. So this represents the angular frequency, at which a parallel circuit experiences resonance. That is, its net reactive component becomes 0. Now clearly, When you substitute this expression in the expression of Z that we just wrote down, you get Z equal to L by RC. This L by RC, interestingly, is the maximum value of Z. So the weird part is that in case of series resonance, at resonance, Z is minimum. But in case of parallel resonance, at resonance, Z has its maximum magnitude. Fascinating, but this is perfectly true. One important thing that we must remember, however, is that this quantity under the square root must be greater than 0. So that is another important condition for parallel circuit resonance. Understood? So 1 by LC must be greater than R square by L square, isn't it? Or you can say that R should be less than square root of L by C. So this is the important condition for resonance in a parallel circuit. R should be less than square root of L by C, and omega naught should be square root of 1 by LC minus R square by L square. Of course, you have to remember all this. Now that we've discussed so much about series AC circuits and parallel AC circuits, let's actually draw the phasor diagrams for both the circuits and compare what happens to each quantity in each circuit. In case of a series AC circuit, as you can see, the current is initially along the x-axis. The resistance is in the same direction. The phasor of the resistance is in the same direction. VR, the voltage across the resistance, is in the same phase as the current. The voltage across the inductor leads the current by 90 degrees. Similarly, XL, the inductive reactance, leads the resistance by 90 degrees. VC, the capacitive voltage, lags behind the current by 90 degrees. And here you can see that XC, the capacitive reactance, lags behind the resistance by 90 degrees. In a parallel AC circuit, things are different. Here, the current through the resistor is along the x-axis, and V, the net voltage, of the parallel circuit, because the potential difference across all the elements is the same in this case. So the net potential difference is in the same phase as the current through the resistor. Similarly, you can see that the current through the inductor in this case leads the current through the resistor by 90 degrees. The current through the capacitor lags behind the current through the resistance by 90 degrees. Similarly, XL, the inductive reactance, again leads the resistance by 90 degrees, and XC, the inductive capacitance, again lags behind the resistance by 90 degrees. So basically, if you draw all these graphs and charts, you'll get your final answer easily. Phasors are so very important in the chapter alternating current. The parallel resonance circuit is often called the rejector circuit, as it rejects the resonant current out of all the others. You see, as I just told you, the impedance in case of resonance is maximum. So the resonant frequency is the one that is rejected in case of a parallel circuit. Remember, I was telling you that in case of radio stations and in case of series resonance circuits, only the resonant frequency is accepted. In the case of a parallel resonance circuit, the resonant frequency is rejected. Exactly how is it accepted, how is it rejected, is beyond the scope of our course. But for now, you have to remember that the parallel resonance circuit is called the rejector circuit. Let's now try to calculate the average power dissipated in an AC circuit. It's easy to calculate the power dissipated in a DC circuit. If you have a DC battery like this, and if you have a resistance connected to the DC battery, clearly VI represents the power dissipated in this resistance, isn't it? There's no doubt about it. It's very easy too, because the value of V is constant, I is constant. You simply multiply V by I. In the case of a series AC circuit, for example, however, the power dissipated at any instant is still VI. But the issue is that V and I are not constant. After all, we know that I is I naught sine omega t, and if V leads I by a phase phi, in that case V is V naught sine omega t plus phi. And so the power dissipated at any instant will be V naught I naught sine omega t into sine omega t plus phi. So phi is constant, but the time keeps on changing. At different times, the power will be different. We generally calculate the average value of the power. Instead of quoting instantaneous power, we calculate the average over one time period here. The power consumed varies with time. Now to calculate the average value of the power, we again make use of the expression that the average value of a function with respect to x is integral f of x dx divided by integral dx. In this case, the average value of power is integral p of t dt divided by integral dt. We will integrate from 0 to pi here because the period of this expression sine omega t plus phi comes out to be pi. Interesting, but that's how it happens. So we will integrate from 0 to pi. When we do that, this is the final expression that we get. This one. And when we simplify this expression, this is the final value of the power that we get. In simplifying this expression, we haven't used any complex trigonometry. All we've written is that 2 sine A sine B has been replaced by this expression of 2 cosines. The average power comes out to be Vi cos phi by 2, where phi is the phase difference between the voltage and the current. So if the voltage leads the current by phase phi, the average power at any instant can be taken to be Vi cos phi by 2. Now Vi by 2 can be written as V by root 2 into I by root 2. So you can basically say that the average power is Vrms Irms cos phi. That's an interesting way to represent power, isn't it? But this is true. Of course, this expression is very, very important. You have to remember it. In the case of only a capacitor circuit, the average power is 0. We just said, that average power is Vrms Irms cos phi. But in the case of a capacitor, the phase angle between the current and the voltage is 90 degrees and cos 90 degrees is 0, isn't it? So in this case, the average power is 0. What that means is, that even though current is flowing in the capacitor circuit, no power is consumed. No power is dissipated. Similarly, even in the case of an inductor circuit, cos phi is 0. That's because, phi is 90 degrees, the angle between the voltage across the inductance and the electric current is 90 degrees because the voltage leads the electric current by 90 degrees in the case of an inductor. So again, the inductor current is also a wattless current because as you can see, no power is dissipated to make current flow in an inductor circuit. So that's an interesting phenomenon. Let's solve a problem. An LCR circuit with a 200 ohm resistance is connected to an AC source of 250 volts and angular frequency 400 radians per second. When only the capacitance is removed, the current lags behind the voltage by 30 degrees. When only the inductance is removed, the current leads the voltage by 30 degrees. Find the power dissipated in the circuit. Now this question appears very complicated at first glance. After all, what is happening in this question? Well, in this case, finally, we have to calculate the power dissipated in the circuit. We just read that the power dissipated in the circuit is Vrms Irms into cos phi. The value of Vrms is given, isn't it? Because the AC source is given to have a voltage 250 volts. Irms is not given, and similarly phi is not given. But to calculate Irms and phi, so many conditions are given in this question. So let's look at each condition and try to calculate Irms and phi. First, let's look at the first condition. It is given that when the capacitor is removed from this LCR circuit, in that case, the voltage leads the current by 30 degrees, isn't it? Now, if the voltage leads the current by 30 degrees, that means that tan 30 degrees is also equal to XL divided by R, isn't it? There's no doubt about it. After all, if the voltage leads by 30 degrees, in that case, the net impedance consisting only of L and R also leads the resistance by 30 degrees. So XL by R is tan 30 degrees, or XL is R by root 3. Similarly, it is given that when the inductance is removed, the current leads the voltage by 30 degrees. This again tells us that XC by R is tan 30 degrees in the opposite direction, isn't it? And XC is R by root 3 again. This is again because if the current leads the voltage by 30 degrees, that means that the resistance leads the impedance consisting of R and C by 30 degrees, and that's why I've written XC by R is tan 30 degrees. So we have found out that the value of XL is R by root 3 and the value of XC is also R by root 3. Now XL and XC are the same, and we know that Z is square root of R square plus XL minus XC whole square. So Z is basically R in this case because XL equal to XC, and therefore this circuit is already in resonance because the net reactive component of this circuit is 0. Now since this circuit is in resonance, it is very easy to calculate its average power. The average power is Vrms Irms cos phi. Now phi is 0, that's because the reactive component is 0. So the net angle between the voltage and the current will be the same because L and C do not contribute to the net potential drop. Irms is clearly Vrms divided by Z, and since Z is R, we can say that Irms is Vrms divided by R. Vrms is given to be 250 and Z is given to be 200. So I comes out to be 1.25 amperes. What is Vrms? It's given to be 250 volts. And therefore on simplification, the value of the average power of the series LCR circuit comes out to be 312.5 watts. Net power 312.5 watts on an average is consumed as this circuit operates. Again, in most AC circuit problems, you only have to see, what do I have to find out? And then you go about applying the conditions given to find out what you have to find out, isn't it? And of course, a good knowledge of phasors is very, very useful. Let's now proceed to the next interesting concept that we're going to study, the concept of a choke coil. Now you see, we had just discussed that in case of an inductor and a capacitor, zero power is consumed, isn't it? The average power dissipated is 0. What that means is that even if we change the current in the circuit, the net power consumed by the inductor or the capacitor will be 0. In a choke coil, we make use of this phenomena to have different currents in the circuit and still maintain the same level of power consumption. Understood? And that's very interesting. For example, a choke coil is basically used to reduce the current without much loss in power. A choke coil consists basically of an inductor. Now if you take a tube light and if I switch on this tube light, this one that you see here, the tube light is getting switched on. This box here, remember the box that's present in all tube lights is the choke coil. The choke coil basically consists of an inductor, as I just told you. When the tube light is off, a lot of current is initially required to start the tube light. But once the tube light has been switched on, less current is required later. However, it is important that the same amount of power be consumed, even when the tube light is just getting on and even after some time when the tube light has started. So we want, lesser current but the same amount of power. Now, what promises us that? An inductor or a capacitor. So we use an inductor in this case because as you can see, the power does not change when you add an inductor to a circuit, isn't it? So we add an inductor in parallel with the tube light circuit. Understood? And therefore, the power of the circuit does not change, but the current in the circuit decreases, isn't it? Because after all, the inductor takes in some current. So here we go. If you magnify this picture, this is what is inside the choke coil. There is this inductor and there is this alternating voltage source, and that is all. So what you really must remember about the choke coil is that it is used to reduce the current while it keeps the net power consumed as the same, and makes use of the fact that the net power consumed in an inductor or a capacitor is 0 on an average. And this concept actually brings us to the end of the chapter relating to alternating current. There we go. So since the flux passing through this coil is Bs cos omega t, therefore we can calculate the induced EMF in this coil. We already know that the EMF through the coil will be minus d phi by dt, isn't it? Because when flux varies, EMF is produced. And so d phi by dt will be Bs omega sin omega t. And if you observe carefully, you can see that basically the net EMF induced is proportional to sin omega t. That means that the net EMF produced is a sinusoidal function, isn't it? So this is how an alternating current, which keeps on varying periodically, can be produced.
And that is how alternating voltage and alternating current are produced. Understood? So there you go. You might find it to be a bit tough, but you only need to understand the crux of this concept. You don't need to delve into the inner details of this concept here. Basically, alternating current is produced when there's a magnetic field and a coil is rotated in the magnetic field, and because of that rotating coil, an EMF that's proportional to sin omega t is produced. Understood? Omega, of course, here is the angular frequency of rotation of the coil. Whenever we use alternating current in our circuits, this is the symbol we will use to represent alternating current. V is V naught sin omega t, and I is I naught cos omega t or I naught sin omega t. So these will be the values of alternating current or alternating voltage that will be mentioned in all your IIT JEE and other problems. And the symbol that will be used will be this symbol. If you are shown this symbol in a circuit, the current flowing is not DC but AC. Understood? Now what is omega in these formulae? If we write V equal to V sin omega t as the alternating voltage, then what is omega here? You see, omega is obviously the angular velocity of the coil that was rotating to create this alternating current. But omega is also 2 pi into F. That is, omega represents 2 pi times the number of cycles the alternating current completes in 1 second. So you see, if the alternating current is something like this here, in that case, as you can see, the current varies like this from 0 here to say a time t here. Now the variation is repeated. The current again varies the same way, isn't it? So this one single variation of the alternating current, which keeps getting repeated again and again and again, is actually called the time period of variation. And it's called one cycle. So the number of cycles happening in 1 second is the frequency of the alternating current. So as you can see, the value of the current first increases, then it reaches its maximum value, then it decreases, then it further decreases and increases in the opposite direction, and then finally the current again comes in the same position as it was at the beginning. So as you can see, the same cycle keeps getting repeated in the case of alternating current. Now the number of such cycles repeating in 1 second is called the frequency of the alternating current, and the time in which one cycle of the alternating current is completed is called the time period of the alternating current. Omega is a special quantity, whose significance we will learn later. But for now you can understand that omega is 2 pi times the frequency. That is 2 pi times the number of such cycles repeated in 1 second by the alternating current. Understood? In India, the value omega by 2 pi, which is the same as the frequency of the alternating current, is generally 50 Hz. What this means is, that the current that you use to light up your bulbs, tube lights, computers and televisions actually has, the same cycle repeating 50 times in 1 second. Understood? It increases, decreases and then again increases 50 times in 1 single second. One fascinating thing that we are going to learn now is the process of calculating the average value of the alternating current. You see, the alternating current increases, decreases, increases again. So what's the average value of the alternating current? In general, to calculate the average value of a varying function, say a function varies with x, then to do that, we use the formula, the average value is integral f of x dx divided by integral dx. What this means is, that if the speed of a particle is say 3t plus 2, so the speed of a particle is basically varying with time. In that case, the value of average speed can be written as integral v of t dt divided by integral dt. Understood? And of course, we'll integrate, between the two limits in which we have to calculate the average value of the quantity. Understood? So for example, in the case of current, we know that current is I equal to I naught into, say, sine omega t, isn't it? In that case, we can basically say that the average value of the alternating current will be integral I of t dt divided by integral dt, isn't it? So that's how we can generally calculate the average value of a function that varies with respect to x or t. Of course, we'll not derive exactly how we got this, formula for calculating average values, because that is beyond the scope of our competition syllabus. Understood? The next fascinating quantity that we can calculate is the RMS value. The RMS value is the short form of root mean square value. The RMS value is generally also used to, determine what the value of a varying quantity is. For example, if I is I naught sine omega t, then what is that one quantity that can represent the entire variation? That will be the RMS value. You can basically assume that it's a different way of calculating the average. It's a different kind of average, in fact. Now, the RMS value of a function f of x is given by the formula square root of integral f square x dx divided by integral dx. So you must again remember this formula. The RMS value of a function is square root of integral f square of x dx divided by integral dx. As you can clearly see, the RMS value is basically just another way of calculating, a different kind of average of a varying function. Understood? The RMS value is useful sometimes when the average value of a quantity is 0. You see, for example, if a quantity is increasing also, decreasing also, increasing also, in that case the average value of that quantity could be 0. But we want to make out what value the quantity has most of the time. In that case, we use this root mean square value. So let's try to calculate the average values of the current and the voltage, and also the RMS values in the case of alternating current. So let us first try to calculate the current in a complete time period. So let's say the current is varying like this with respect to time. As you can see, I is I naught sine omega t. The current is 0 at time t equal to 0. Then the current increases, and finally, at time equal to pi by omega, the current becomes 0 again. Then it decreases, reaches a negative maximum value, and then again it becomes 0 at 2 pi by omega time. So from 0 to 2 pi by omega, the current completes one cycle. Then the same cycle keeps repeating again and again and again. So let's calculate the average current from time equal to 0 to t equal to 2 pi by omega, isn't it? Because that will be the average current in one cycle, and the average current in one cycle will be the average current throughout time, because the same cycle keeps repeating again and again. So the average value of the current in the complete time period is clearly integral 0 to 2 pi by omega I naught sine omega t dt divided by integral 0 to 2 pi by omega dt. After all, in this case, f of t dt is I naught sine omega t dt, isn't it? And dt is dt. So we've used the same formula, that we just discussed to calculate the average current in the complete time period, in one cycle. Now, when we simplify this expression, we get the value for the average current in the complete time period as 0. This is interesting, isn't it? But this is true too. So the average current, from 0 to 2 pi by omega, from 2 pi by omega to 4 pi by omega, and so on, is 0. And that brings us to an interesting conclusion. The average current in a complete time period is of no use to us. That's because, we know that there is some current flowing, the current is increasing and the current is decreasing. So, on an average, what will be the value of current, if at any random instant you check the value of current? To help find such a non-zero value, we calculate the average current in half a time period. That helps us determine the average magnitude of the current. Again, to calculate the average current in half time period, we use the formula integral 0 to half of time period f of t dt divided by integral 0 to half time period dt. So we'll say that the average current in half a time period, that is from 0 to pi by omega, is integral 0 to pi by omega I naught sin omega t dt divided by integral 0 to pi by omega dt. When we simplify this expression, we get the value of the average current in half a time period as 2 I naught by pi. What this means is that the current from 0 to pi by omega has an average value 2 I naught by pi. Similarly, the current from pi by omega to 2 pi by omega has an average magnitude 2 I naught by pi, and so on. Now this measure, calculating the average current in half a time period, is definitely a much better way to go about calculating the average value of current. That's because what will we do with a current value of 0? That is of no practical significance. So yes, when we have to calculate average current, we use half a time period in the case of alternating current. Many times, however, instead of using the average current values at all, we use the RMS current values. The RMS current values, overall give a correct version of what the mean value of the current at any time t is. Understood? So, to estimate how much current is flowing at any time, you can assume the RMS value to be the most accurate value that tells you at any time what current is flowing in a circuit. To calculate the RMS value, we use this formula. IRMS is clearly square root of f of t square dt divided by integral dt. So we'll say, IRMS is square root of integral 0 to 2 pi by omega I naught square sine square omega t dt. I've simply squared the expression I naught sine omega t, isn't it? Divided by integral 0 to 2 pi by omega dt. In this case again, when I've written integral 0 to 2 pi by omega, I've made sure that we've calculated the RMS value throughout the entire time period. So this RMS value is being calculated from 0 to 2 pi by omega, from 0 to 1 time period. Understood? The final value of the RMS current on simplification comes out to be this expression. IRMS is I naught by root 2. So whenever you're given the RMS current, what that means is that you are given 1 by root 2 times the maximum value of current in one time period. Understood? I naught, as I just mentioned here, tells you the maximum value of the current at this position, or say this position or this position. The RMS value of the current is also called the effective current. We generally mention voltage values like 230 volts when we talk about household supplies. The 230 volts there is the RMS value of the voltage. Understood? RMS values are used to perfectly approximate the value of current or voltage when it varies periodically with time.
Now let's move on and study some simple AC circuits. The first AC circuit that we will study is definitely the R circuit. The R circuit consists only of a resistance. So for example, this is the R circuit in front of you on your screen. There's this AC voltage and there's this resistance R connected to the AC voltage. So what will be the relationship between V and R in this case? If we assume that the current varies sinusoidally, and I is I naught sin omega t, then V will be clearly IR, isn't it? And IR is I naught R sin omega t. There is no doubt about that, because I is I naught sin omega t, isn't it? And therefore, I naught R can be replaced by V naught, and you can write that V is V naught sin omega t. Understood? An interesting fact here is, that you can make out clearly that V naught equal to I naught R. That is, the maximum value of voltage here is equal to the maximum value of current into the resistance R. And therefore V naught by root 2 is equal to I naught by root 2 into R. So VRMS equal to IRMS into R. So you can simply apply Ohm's law even in the case of alternating current circuits. The only difference here is that in the case of DC circuits, you can apply Ohm's law directly and say V equal to IR. In the case of alternating current circuits, you have to calculate the RMS value, and then you can say that VRMS is IRMS into R, isn't it? Of course, you can also consider V and I at general points, and at any instant you can again apply Ohm's law and say that V at any instant equal to I at that instant into R. So there, if you sketch a graph here, of the voltage as it varies with time in the case when only a resistor is connected, and if you draw a graph of the current as it varies with time if only a resistance is connected, you will get two graphs like this. As you can clearly make out, the time period of both the current's variation and the voltage variation is the same. Similarly, both the waves are in phase, isn't it? That means that the variation of the current and voltage is in phase. Both of them have the same zero, isn't it? Both of them are zero at exactly the same intervals, isn't it? And at exactly the same points. So both of them are said to be in phase, isn't it? Because their time period is the same, and the exact starting point and ending point of each cycle is the same. So that was about the current and voltage in a simple AC resistance circuit. Now to further explain AC circuit details better, we define quantities called phasors. Phasors are interesting quantities that make calculations in AC circuits very simple. So let's say you have this graph I equal to I naught sin omega t. This represents the variation of the electric current I with respect to time. There's no doubt about it, is there? Now you can see that this graph here represents the variation of I with respect to time. I increases, as you can see on the graph, and on the right side here I decreases. I becomes 0, and then I increases again, then I decreases again, then I achieves its negative maximum value, I becomes 0 again. So as you can clearly see, the graph on the left basically depicts the variation of electric current with respect to time. As time keeps on going on, the electric current first increases, then decreases, then it increases in the negative direction, then it again decreases and becomes 0, and the cycle continues. As you can see, the brown line on the right here represents the variation in the magnitude of electric current with time. Now we can actually represent this variation of electric current with the help of a phasor diagram. A phasor diagram basically consists of a vector whose magnitude is equal to I naught, the maximum value of electric current. Now the point is that as electric current increases and decreases, the phasor vector keeps rotating in a circle. How can that happen? Well, you see, the motion of the current is periodic. The current increases, it becomes 0, then it decreases and achieves a negative maximum value, then it becomes 0 again, and that completes one cycle. Similarly, the phasor vector rotates around a certain point and completes one cycle in exactly the same time as one cycle completed by the electric current, in increasing, decreasing and increasing again. So for example, here, as the electric current decreases, the phasor vector rotates, it becomes 0, the phasor vector keeps rotating, and here you can see that the phasor vector completes one rotation in exactly the same time as the electric current completes one cycle, isn't it? There you go. So basically what we've done is that we've represented the variation of electric current as a vector which keeps rotating, about a certain point. Understood? Now the angle that this phasor vector makes with the x-axis is taken to be omega t. If you notice the component, the vertical component of this phasor vector, what is the vertical component? Clearly I naught sin omega t, isn't it? And as you can see, it corresponds with the amplitude of electric current at any instant, isn't it? After all, the magnitude of this phasor vector is I naught, so its component along the x-axis will be I naught cos omega t, and along the y-axis it will be I naught sin omega t. So
The component of the phasor vector along the y-axis represents the actual magnitude of the electric current at any instant, that is I naught sin omega t, isn't it? And that is why the angle that the phasor vector makes with the x-axis is taken to be omega t. Now this concept related to phasors may sound very tough and difficult at first. But just understand that all we're trying to do is that we're trying to represent periodic motion by means of a vector which keeps rotating in a circle. Now this vector rotates in such a way that at any instant it makes an angle omega t with the x-axis. Understood? And this angle omega t is such that I naught sin omega t is the displacement at that instant when the angle made with the x-axis is omega t, isn't it? And the magnitude of the phasor vector is I naught. So I naught sin omega t, as you can clearly see, is the magnitude of the electric current at that instant. Now don't be worried, if you do not grasp the concept of phasors immediately. It is a bit tough. However, as we move on, we'll use phasors so often that you'll definitely, grasp the concept of phasors easily by the end of this chapter. Again, let's say this is I1 equal to I naught sin omega t. This is the graph of variation of electric current with respect to time. Let's say there's another electric current which has this graph I equal to I naught sin omega t plus phi. In that case, this will be the graph of the second electric current. The point I want to make here is that when you are given two electric currents, I equal to I naught sin omega t and I equal to I naught sin omega t plus phi, in that case this plus phi here indicates the phase by which the second current leads the first current. As you can see, at time t equal to 0 here, the first current has value 0, but at time t equal to 0, this second current already has some value, isn't it? And therefore you can say that it leads the first current by a phase phi. Phi is the initial phase of the second current. Let's see what difference in phasor diagram will occur if a certain current leads another current by a phase phi. You see, if phi equal to 0, in that case both the electric current phasors will start from the x-axis. As you can see, this white arrow here is along the x-axis, isn't it? So phi, the initial phase, is 0. Now if phi is pi by 2, what that means is that the first vector starts from the x-axis and starts rotating in the anti-clockwise direction, but the second vector starts from phi equal to pi by 2. That is, it starts here. Understood? So it starts at an angle 90 degrees greater than the first vector. Understood? So phi represents the angle by which the phasor of the second vector leads the first vector. Understood? So there you go. This vector's motion will start from phi equal to 90 degrees here, isn't it? Similarly, if phi is pi, then the motion of this vector will actually start like this. Understood? It will start from an angle pi, and therefore it will lead the first vector by an angle pi. Now the motion of both the vectors will be the same, the phasors will be the same, the pattern will be the same, the time period will be the same, the number of cycles per second will be the same. However, at any instant, the electric current in the second case will be a phase phi ahead of the electric current in the first phase. Understood? Don't get too confused about, quantities like omega and phi. For example, you might think, what exactly does omega represent? What exactly does phi represent? Isn't it? So, I can tell you that omega t basically represents the angle by which the phasor vector rotates at any instant t. Phi indicates the angle by which the phasor vector has rotated already at time t equal to 0. Understood? That's what phi represents. So there you go. We've understood the basics of phasors. So in case of R circuits, for instance, you can see that I is I naught sin omega t and V is V naught sin omega t, isn't it? So as you can see, there's no phase difference between I and V. The voltage does not lag behind the current, or it does not lead the current in phase, isn't it? As you can see, both the voltage and the current, they start at the same time and they end at the same time, isn't it? The current and the voltage are in the same phase.
both the current and voltage attain their maximum value at the same instant. Both current and voltage again become zero at the same instant. They again attain their most negative point at the same instant. And throughout their cycles, the phase for current and voltage is exactly the same. If you actually look at the phases of the current and voltage, both of them are actually along the x-axis, isn't it? These phases of course keep rotating with respect to time, but at time t equal to 0, both the phases are exactly aligned along the x-axis. The current does not lead the voltage, or the voltage does not lead the current, isn't it? Because both of them are in the same phase. There's no omega t plus phi factor. Let's now look at another kind of circuits. Let's now look at C circuits. C circuits are circuits which have a capacitor and an alternating current source connected to the capacitor, isn't it? In this case, let's calculate the relationship between I, the current in the C circuit, and V, the voltage of the C circuit. So in the case of capacitive circuits, how do we find out the relationship between V and I, the alternating voltage and the alternating current? Well, in this case, what we do is, we simply apply Kirchhoff's law. You see, according to Kirchhoff's law, V minus Q by C is 0, isn't it? So we say V minus Q by C is 0, where Q is the charge on the capacitor and C is the capacitance of the capacitor. Now Q here can be written as integral I dt, isn't it? There is no doubt about it. After all, dq by dt is I, so Q must be integral I dt. So V is integral I dt by C. Now I can be replaced by I naught sin omega t. So V is I naught by C, integral sin omega t dt. Understood? When we simplify this expression, we get the value of V as I naught by omega c into minus cos omega t. Or we can finally say that V is V naught into sin omega t minus pi by 2. So this is the expression for the voltage of a capacitor circuit when you already know that the current is I naught sin omega t. Now one fascinating thing here is that the potential difference here, or the voltage here, lags behind the current by pi by 2, isn't it? That is clear from this blue box that you see on your screen. So there, the expression for the voltage says sine of omega t minus pi by 2. And therefore, when you draw the phasor diagram in this case, voltage lags behind current. So this is a fact that you have to remember, that in case of all capacitor circuits, the voltage lags behind the current by an angle pi by 2. So if this is the graph for the current, I is I naught sin omega t, then this will be the graph for the voltage. V is V naught sin omega t minus pi by 2. What you can see here is that current is always an angle pi by 2 ahead of the voltage. For example, this green line here represents voltage and the blue line represents current. You can see that the cycle for the current starts from the origin, but the cycle for the voltage starts later, at the point when the current is maximum, isn't it? Cycle for the voltage starts here, isn't it? So you can say that the values of the voltage and current are one and the same for a point that's pi by 2 behind the current. Similarly, current and voltage are not maximum at the same time. When current is maximum, the voltage is still pi by 2 behind. So if you draw phasor diagrams, this is how the phasor diagram will be. As you can see, initially at t equal to 0, the phasor diagram shows that the current is along the x-axis, isn't it? Its phase is 0. However, the voltage is pi by 2 behind the current. That's why you see that the voltage is along the negative y-axis, isn't it? In competitive examinations, many times you will be shown a lot of curves. So how will you get to know, just by looking at the curve, if one curve is ahead of the curve by say 90 degrees or 45 degrees, or if that curve lags behind the other curve by 90 degrees or 45 degrees. Like, can you look at the graph of two curves and immediately make out and say that this curve leads and this curve lags behind? Well, the simplest technique to make that out is to look at the cycle of the curve. If you look at the graph of the current here, then this is the cycle of the curve, isn't it? The curve starts here, then it increases, then decreases further, assumes a negative value, and finally becomes 0. Now if you observe this same exact curve for the voltage, then this is that curve, isn't it? Here it starts here. So what you can see is that the same curve starts at a later position, isn't it? For the current, this curve here started here at the origin, but for this green line, for the voltage, this same cyclic curve, it started here sometime after current's curve started. So you can say that since the cycle of the voltage has started slightly after the cycle of the current has started, you can say that the voltage lags behind. Understood? So there you go. In case of capacitors, voltage lags current by pi by 2. Of course, you can always note that V0, the maximum voltage in this case, is I0 by omega c. In the equation that we just derived, we just wrote that V is V0 sin omega t minus pi by 2. We had just derived that V0 is I0 by omega c. What that means is that the maximum value of the voltage is the same as the maximum value of the current divided by omega c. Now the interesting thing is that we generally try to think of 1 upon omega c as a resistive term, a term that basically resists the flow of current. After all, if this were a purely resistive circuit having only a resistance, we would have said that V equal to IR. In this case, we are seeing that V0 is I0 into 1 upon omega c. So 1 upon omega c is generally replaced by XC, and XC is also called the capacitive reactance. Understood? So the capacitive reactance, represents for a capacitor what resistance represents for a resistor. Understood? Vrms equal to Irms into Xc. You can say V0 is I0 into Xc, isn't it? Where Xc is 1 upon omega c. The interesting thing here is that Xc is always in phase with the potential difference across the ends of the capacitor. What this means is that if the voltage lags behind the current by 90 degrees, Xc, the capacitive reactance, also lags behind the current by 90 degrees. And interesting, isn't it? But this is true. So the capacitive reactance can also be represented by a phasor vector in the same direction as the voltage. So that was about capacitive circuits. Let's now move on to inductor circuits. Here's an inductor circuit on your screen. Again, I is I0 sin omega t. Applying Kirchhoff's law, we can say that V minus L di by dt is 0. We can substitute I here by I0 sin omega t, isn't it? And then differentiate that I to get di by dt. That simplification gives us the value of the potential difference across the inductor as omega L cos omega t. When we further simplify this expression, we get V equal to V0 sin of omega t plus pi by 2. Interesting, isn't it? What we can clearly deduce from this expression is that in case of an inductor, the voltage leads the current by an angle pi by 2, isn't it? After all, I is I0 sin omega t and V is V0 sin omega t plus pi by 2. So you must remember this important fact that in case of an inductor, the voltage always leads the current. So again, if this is the graph for the current, I is I0 sin omega t, the voltage leads the current. What that means is, that the graph for the voltage will be something like this. You see, again, you can make out exactly which curve leads and which curve does not lead quite easily. Observe this part of this curve, this one, this depression part of the green curve, and then, this part here. This can represent one cycle of the green curve, isn't it? If you extend this curve further. However, this same cycle, starts later for the current. It starts here, isn't it? The green curve attains this lower depression earlier, and the blue curve attains the lower depression later. So the blue curve lags behind the green curve, or the current lags behind the voltage, which is true. The current in an inductor lags behind the voltage by pi by 2. If you again try to sketch the phasors for the current and the voltage. The current will of course be along the x-axis, because any expression which says I equal to I naught sine omega t will be along the x-axis, isn't it, at time t equal to 0. Now since the voltage leads current by pi by 2, initially at time t equal to 0, the voltage phasor will be like this. It will be along the positive y-axis. Understood? So that's very important. Again, in this case too, when we derived the expression, we saw that V0 was I naught into omega L. Again, this expression can be compared to the expression V equal to IR in the case of a resistance circuit. And therefore, omega L is given the name, XL. And it's also called the inductive reactance. Understood? So, the equivalent of resistance in case of a capacitor is, capacitive reactance. For an inductor, the resisting factor is called inductive reactance, isn't it? And Vrms will be Irms into XL. Similarly, V0 will be I naught into omega L. XL, by the way, can also be represented by a phasor. And the XL phasor leads the current by 90 degrees. Understood? So, XL leads the current by 90 degrees, and XC, the capacitive reactance, lags behind the current by 90 degrees. Fascinating, isn't it? Let's move on to an even more complex concept. I know things are just getting tougher and tougher, but just keep reading, keep watching, and soon, when we practice using our problems, you'll get a hang of what's happening. Now, what will happen, if you connect a resistor and an inductor and a capacitor to an alternating current voltage source? That would be interesting, isn't it? Let's try doing that. And then let's try to calculate the relationship between the voltage and the electric current flowing in the circuit. Let's try to see whether the voltage leads the current or the current leads the voltage, and by what angle. And also, let's try to draw the phasor diagrams. VR can represent the voltage across the resistance R. VL represents the voltage across the inductor L. And VC represents the potential difference across the capacitor. Now again, since this is a series circuit, one single current will flow through the resistor, inductor and capacitor, and this current has been assumed to be I naught sine omega t. Okay. Now, in the phasor diagram, I naught sine omega t, or the current I initially at t equal to 0 will be along the x-axis, isn't it? There's no doubt about it. Now, VR, the potential difference across the resistor, will be parallel to I, isn't it? After all, we had just discussed that in case of a resistor, the voltage and current are in phase, isn't it? We had discussed that when we had discussed a purely resistive circuit. So VR and I will be in the same direction. VC phasor, however, will lag behind I by 90 degrees, because we had again discussed that the capacitive voltage lags behind the current by 90 degrees. Similarly, initially, VL will lead the current by 90 degrees. That's because, again, as we had just discussed, the inductor voltage leads the current by 90 degrees. Now, these are basically vectors. After all, we are representing voltage and current by phasor vectors. Therefore, if we add up these vectors, this is what we get. When I add up VL vector and VC vector in the opposite direction, I get a single VL minus VC vector upwards, isn't it? And so the net voltage across all these elements will clearly be the vector sum of VR and VL minus VC, isn't it? And since, V makes an angle phi with the electric current, you can say that the net voltage of an RLC circuit actually, leads the current by an angle phi, where phi is VL minus VC by VR, isn't it? You can make that out from this phasor diagram, isn't it? You see, phasors can be treated exactly like vectors once you represent current and voltage quantities as phasors. Understood? So again, the magnitude of the net voltage in this case will be square root of VR square plus VL minus VC whole square, isn't it? After all, the hypotenuse is square root of side 1 square plus side 2 square, isn't it? So this will be the expression for the net potential difference across the circuit. All we have done is that we've replaced the potential difference across each element by a phasor and then vectorially added the phasors. Of course, the value of VR will be IRMS into R. The value of VL will be IRMS into XL, and the value of VC will be IRMS into XC. After all, the voltage keeps varying. So which voltage do you take when you write I, VR, VL, VC? In general, if we are replacing the entire voltage by say one quantity, then we are taking RMS values. Understood? Tan phi, as I just said, is VL minus VC by VR. When we calculate the value of phi, we will get the value by which the net voltage in this RLC circuit leads the current. So say if the value of phi is 30 degrees, that means that the voltage leads the current by 30 degrees for this particular RLC circuit. Now we just wrote that V is square root of VR square plus VL minus VC whole square. Now VR, the voltage across the resistance, is IRMS into R. VL, the voltage across the inductor, is IRMS into XL. And VC, the voltage across the capacitor, is IRMS into XC. When we simplify this expression, we get the value of V by IRMS as this expression, square root of R square plus XL minus XC whole square. Now what does V by IRMS represent? In general, if it were a purely resistive circuit, V by I would have represented the value of the resistance, according to Ohm's law. In this case, V by IRMS represents a special quantity called impedance. Just as resistance represents the resistance to the flow of electrons in an ordinary, only resistance circuit, impedance represents the same resistance to the flow of electrons in a circuit containing R, L and C. Understood? It's the impedance to the path of the current. So Z is square root of R square plus XL minus XC whole square. Of course, you have to remember this expression for Z. One fascinating thing about Z, however, is that you can actually represent Z as a phasor. You see, as I had said earlier, XL can be represented as a phasor that leads the current by 90 degrees. XC can be represented as a phasor that lags behind the current by 90 degrees. Similarly, R, the resistance itself, can be represented as a phasor that's exactly in phase with the current and parallel to the x-axis. So R is parallel to the x-axis. XL points upwards and XC points downwards. And therefore, the net sum of the two reactances and of this resistance comes out to be the vector sum of R and XL minus XC. As you can see, Z represents the vector sum of R and XL minus XC. As you can again make out, Z is square root of R square plus XL minus XC whole square, isn't it? From this diagram also, because again, hypotenuse is square root of side 1 square plus side 2 square. We are basically calculating the magnitude of the resultant vector of R vector and XL minus XC vector. Tan phi, the angle by which the phase of the impedance leads the current, is XL minus XC by R. So if the value of phi comes out to be 30 degrees, that means that the net impedance of the circuit actually leads the current by an angle 30 degrees. Understood? So this is very, very interesting. The fact that you can represent the reactances and the resistance actually as phasors. Again, if it all seems a bit too complicated, don't you worry. The moment we solve the problems, things will become clearer.